Any questions, any comments before I start? Okay. Before I start the exponential and log functions, which I know that you guys have been working with those ones a bit long time, I wanted to do another examples of what we had last time, the trig inverse functions. The one, I think one I did before, yes, so this is cosine of tan inverse of 2 over 5. And there is a question, actually, I posted on the lecture notes. Find the domain of this function. Okay, go ahead, please. Maybe 1 minute. This is a good chance to review quickly. You definitely need to talk to the friend sitting next to you. And any discussion, anything related to those is going to be, those two questions is going to be helpful. Go ahead, your 1 minute starts now. What? You have 30 seconds left. Okay. See, last time we did some examples for this, yes? If your trig function and trig inverse function that you're composing, they're the same thing, you're trying to use the rules of inverse function. For example, if I have sine inverse of, say, whatever number you like root 2. Oh, root 2 cannot be there. Root 2 over 3. Yeah? Here you have sine and sine inverse. If you compose a function with its inverse, they will cancel each other because that's how the inverse works. Reverse is the thing. The only thing you need to be worried about is that the value there, is it in the domain of these guys or not? Whatever the first function is. If that is, in this case, what is domain of sine inverse? Yes, please.
Negative pi over 2 to
Isn't that domain of sine itself? I'm asking for domain of sine inverse. Yes, please. Negative 1 to 1. This is the range of sine, yes? For sine and cosine, the domain is negative 1 to 1. And then you see that, oh, this number is there. So then they will cancel each other. And you get that. Just simple, straightforward. Even if it is the other way around, we did an example here. If you had sine of sine inverse of an angle, you have to try to replace that angle with one of the angles in the interval of 1 to 1 interval, and then apply the same rule. They will cancel each other. For this one, however, the story is different. You have two different trig and trig inverse functions involved. And as we did last time, well, I didn't complete it. I did post the notes for that question. So that's why I'm doing a different question, so you can see more examples. In these cases, the only thing you need is to rewrite what is given there. What I mean is this. I'm looking for cosine of an angle. This is my question, yes? What is cosine of an angle? But we know that that angle is going to be given, is going to be given by this. Yeah? So if I find such a theta and then plug it in here, this will be done. But that's not the actual thing we are going to do. What will this give us is that if such angle exists, or we can find such angle, then the tan theta is going to be 2 over 5. In other words, we are given tan theta, we are asked what is sine theta. You know one, you know all. That's the same story, yes? However, here, there is something that I haven't written down. Can anyone point out what is that? Yes, please. Pardon?
Sorry, no, I was going to say that point if you're doing the triangle method.
We will do that, but before that, let me see if can someone point out. Theta is tan inverse of that. It means this plus another thing. What is that other thing? Without that other thing, actually, nothing will work. Remember that whenever the inverse function, we define inverse function, we restricted our trig functions to one-to-one domain. You have to always use or bring up that one-to-one domain. Restriction. Yes. In the case of tan, what was that restriction? Negative pi over 2 to pi over 2. So theta not only will have that tan, but also it will have this value there. It will be somewhere there. How is that going to help us? Well, this means that our angle is either in the fourth quadrant or on the first quadrant. See, that restriction is going to play a very important role. It's fixing possible quadrants, only 2 of them for us here. But it has something more as well there. We know that tan of 2 over 5, tan of theta is 2 over 5. It's a positive value. And you remember that all students take calculus. If tan is positive, that means that we cannot have our angle in the fourth quadrant. It must be in the first quadrant. All students take calculus, yes? So then we know now everything. We know one ratio. We know in the quadrant. We can find all other trig ratios, including cosine theta. Yes? And the rest you just play with the triangles, or you can use the triangles on the, or you can use, the triangles on the unit circle. Here, I will just go ahead and say, okay, this is opposite, this is adjacent, then here will be 4 plus 25, 29. I have the ratios all there. Cosine of theta will be 5 over this one, either positive of that or negative of that. So this is going to be okay. Is it going to be positive? Should I leave it as positive, or I should make it negative? Positive. Positive. Why? Because all students on the first quadrant, everything is positive, so the cosine is going to be positive as well. Playing with this one-to-one domain of these trig functions, when you work with the trig inverse functions, is the key point. It will appear again and again and again and again. Okay? Any questions, any comments here for me? Okay. One of the things that comes up after, do you have the question?
Just take a photo.
Okay, okay. So one of the things that I mentioned earlier last week was that when it comes to domain, there were two restrictions, yes? The 0 cannot be in the denominator, negative number cannot be under the even roots. Now we have more new restrictions. Remember cosine inverse, when we defined, we ended up having, was it here? Yes, okay, we did work with this. So cosine, domain of cosine inverse, we know that is -1 and 1. And that is another new restriction that you may need to know when you're calculating domain of functions. So domain of f is going to be all x's in the domain of 2x plus 3 such that 2x plus 3 is in the interval -1 and 1. Remember, this is the composition of two things. First, I have to be able to plug in x into this function. So x must be in the domain of that. And second, the value of the inner function must be in the domain of the outer functions, or in other words, I can use it as input into the second function. What is domain of this function here? 2x plus 3. The whole real line. Why? It's a polynomial, yes? So this is x. We have to figure out the other one. In other words, we have to figure out that for what values of x, 2x plus 3 is between 1 and -1, including both ends. Yeah? And then you try to solve it. This is an easy inequality. Actually, you don't need the sign table, but you can use the sign table for this one as well. What I can do is that I can, let me write it over there. Ooh, things are coming out from there. I will use this piece so that I don't get more space. Only when it is linear, you actually don't need to use the sign table. Subtract -3 for all 3 sides. -2. Yes. So -1 minus 3, -3 cancels this one. 1 minus 3, that's the. Now you have a positive 2, so you divide everything by positive, so that will give you this piece. In other words, x must be between -1 and -2. Okay? So that new restriction solves me all the work, all the inequalities, and all the possible values that we are interested in this case, for this function. So summary is that list of 2 restrictions, now you may get more restrictions. For trig inverse functions, you have new restrictions, you have to know them. And you also need to know the restrictions for the inverse of exponential function. That's something that I'm going to do in a second. Any questions, any comments? I know that we did lots of work for trig inverse function, but I wanted to make sure that we covered these 2 cases before I move to the next topic. Exponential functions. Well, you have seen these all before a function of this form, we call it exponential function. Since we don't know how to find exponential powers of negative numbers for all given x's, I need to make sure that b is bigger than 0. There's a small other restriction that I will point out in a minute. So just keep this a little bit empty here so that I will add that other restriction. OK? Well, when you're working with exponential functions, one thing to know is that the domain of exponential functions, you can plug in any number you like there. All the numbers are allowed. So this is the whole real line. For the range, we will need a little bit of work. I mean, but, well, I can draw the graph of these functions, and then you can see from there what is the range of these functions. The graphs there are 3 cases that I have to separate here. And I'm using 3 cases just to show you something interesting, but we will get rid of the middle case, and you will see why. When b is bigger than 1, 2, 3, 10, e, pi, b to the power x. As you increase the exponent, it will get bigger and bigger. In other words, it's going to be increasing. B at x at 0, b to the power 0 is going to be equal to always 1. So actually, all the 3 cases are going to intercept with the y-axis at 1. This one is increasing. And as you make the negative number here bigger and bigger, you get closer and closer to 0. You never touch 0. When b is less than 1, well, obviously bigger than 0, for example, half. Half to the power 2 is smaller than half to the power 1. Because that's a smaller number, you're taking only parts of that smaller number. So that's why this function is going to be decreasing. And again, this goes to 0 as you go to the positive infinity. One case is left. What is that one case?
Needs 1.
Negative I excluded because, for example, negative 1 to the power half. What is negative 1 to the power half? It's square root of negative 1. We don't have such a thing, yes, at least for this code. So that's why we never make it negative. But the case that b is equal to 1. When b is equal to 1, we will erase that. Just keep in mind. I will erase that. I'm drawing it for some reason. When b is equal to 1, I have 1 to the power x. For all x's, 1 to the power x is 1. So I have a constant function. Okay? We are interested in exponential functions that are not trivial. Or I can say when they have inverse. In particular, that means that we are interested only in the cases that we have one-to-one functions. This is one-to-one. This is one-to-one. This guy is failing one-to-oneness awfully. Like, there's no way you can make this one-to-one. That's why we will exclude the case 1 from the basis for the simple reason that that is a singular value for this kind of thing, and we don't want to deal with that. Yeah. Let me see what else, what other properties I have there. Yeah. Oh, once I have the graphs, now I can see the range. Range of a function, if you know the graph, you're basically trying to see what values of y this takes. And you can see that everything above x-axis is received by this sum of these points, and nothing below neither 0. So that means that the range of these exponential functions are going to be that. There is one special case. I want to make sure that you know that one special case. When B is that E, well, they call it different names, Euler constant, Euler, sometimes Neperian constant, they call it. But it's a number. It's a very important one. What is the value of that? Can anyone? 2, yes?
791 or something like that.
2 point, there's a 2.7, what else? 1, I don't know more than that. I cannot confirm. What matters there is that this is an irrational number. So in other words, no matter how many digits I write, I will never be able to express it completely. What is that number? It's a number defined based on the properties that can be explained in the mathematical models or in mathematical problems. But what you need to know is that irrational number, almost 2.7, sometimes when we are doing the estimates, that will be useful. When the base is that specific number, E, we call it e to the power x, is called the natural exponential function. It's natural, it has a reason for that, but you just, most of the time we work with that. Any questions, any comments? Yeah, straightforward. These properties plus properties of exponent. Bx times by is bx plus y and things like that. And I'm expecting that you know those ones. And when time comes, you can use those ones. Now, we want this to be now reversed. We want to find inverse of these functions. Those called logarithmic functions, I will write log functions as the inverse of exponential functions. When we are defining exponential function, we are fixing a base. The same story will happen for the log. The notation here that I'm going to use, f of x equal to log of x base b. So this guy here, we fix it, and then it gives us a function. This is the input of that function. Sometimes I won't put any brackets, so log x base b I will write. But what it is, so if I take y to be log of xb, this means that if you put b to the power y, you will get x. Reversing the exponential function. Someone is giving you a number, x. Now you're looking for a number such that b to the power that number is equal to x. That is how it is defined, or that's how we denote this. It is the inverse of b to the power x. There's only one problem here. If I define inverse of exponential function, what would be domain of that inverse? If I know what is the domain and range of function f, what would be the domain of f inverse? Yes? The range of the function itself. In other words, okay, I'll write this one first thing. Domain of this function f here, log function, is going to be the range of exponential function, which is from 0 all the way to infinity. And that is the new restriction. When you're working with the log function, the input into log function, you should make sure that that is a number bigger than 0. It cannot be 0. It must be bigger than 0. Yeah? Well, since I already have domain, what would be the range of this function?
All real numbers.
The whole real number. Why? Because its inverse had the whole real line as its domain. So when you go to the inverse, you flip the domain and range. Well, now we can draw the graphs of this function. Graphs of inverse function is reflection of these functions with respect to y equal to x. In other words, you flip x and y's. And for b bigger than 1, this will be how it will work. For b less than 1, obviously bigger than 0, it will go. You have to know these functions, and you have to be able to use them when the time's coming. You have to be able to say, yes, I know the graph, so that means this, that means that. Any questions so far? Any questions so far? Yes, please.
I just had a quick question. Why aren't you drawing like colored in boxes beside domain and range?
Oh, I'm trying to say I'm covering some items. This is domain, this is range, these are the graphs, and then so on. This is just like me trying to separate things you can read. It seems that I wasn't very successful in that. Any other questions? The properties of log function, I will list them so that you can see, you can look at them when it is, when you need them. But again, the expectation is that you know all of them. So properties of log. I'll start with the special values. Log of 1 in any base is, log of 1 in any base is 0. B to the power 0 is equal to 1. Also, log of b at base b is 1. B to the power 1 is 1. 2. This is other way of saying that log and exponential functions are inverse of each other. So they cancel each other in some ways. And the way it works is this. If I have log base b, and I have b to the power something, log of b to the power something, but log has the same base as well, they will cancel each other, and you will get that box back. The other way around is also true, which is b to the power log of something base b. Well, we have to make sure that this box is bigger than 0, as we always check this. Otherwise, log doesn't make sense. Log has nice properties when it comes with the, it's called laws of log. So I will put all of them here, 3, 4, 5. Log of product is sum of logs. Log of quotient is difference of, oh, yes, logs. And log and exponential, in some ways it's this property, but I'll make sure to write this. X to the power r base b is r log x base b. So the power inside log can get out of log and become multiple of log. So log of x to the power r is r log x base b. There's one more. I love this one. This is sometimes called change of base, formula for change of base, log of x base b. Historically, people knew that log is important, so they had to find values of log. So they created these tables of log. They had tables of trig functions. They had tables of trig inverse function, things like that. But for log, they only had one base. They didn't have tables for all the bases. To be able to use those tables, you had to know how to change log in one base to another base. And this is called change of base formula. It says that you're interested in finding log of x in base b, pick whatever base that you're okay with, like you can work with. Say base a. Then divide log of x base a by log of b base a. The right-hand side, both of them are in base a. When you divide the left-hand side, you're getting in base b. So that's how you're changing the base. There is a special case, the natural log function. So I should have written this one here. Ln x is what we write when our base is that number e. When the base is e, so this has been, well, out there. This is the standard convention that you don't need to write log base e evaluated at x. You just write ln at x. And you can see that I can change this a little bit more. That's also true. Do this example for me. How about this example? We know that ln of x is 3 and ln of y is 2. Can you evaluate ln of x squared y to the power 4 and what is log of x base y? Go ahead, you need less than 1 minute, but I'm feeling very generous today. 1 minute, you're working on those two. Ln of x is 3, ln of y is 2. Find those two values. Ln of x squared times y to the power 4, ln of x base y. Go ahead, please, and complete that. You have 20 seconds left.
It's basically like.
Okay, yeah, that's better. Okay, let's do this. This is the first thing is that you see products here. Ln is kind of log, yes? It's a specific domain of log. Sorry, specific base of log. So then the same properties works here. Okay? Log sends product to sum. Now, use that last property, property 5, the law of log there. The exponent comes up front and becomes coefficient. 2 ln x, 4 ln y. Now everything down to ln x, ln y. I know that ln x is 3, so 2 times 3, 6 plus 4 times 2, 8. That is 14. And this is just simple ln x over ln y. That's change of base. Ln x is 3, ln y is 2. That's good. I have some time to do more examples. Any questions, any comments before I write that down? Yes, please.
LS property similar to the
log property, yes. So all these things applies. All these things applies for ln. The only thing you have to note here is that the b in all these things, if you replace it by e, those are ln. So all the formulas, all the properties I wrote down there works for ln as well. Okay, then let's do 2 more questions. I like these questions. Find an exponential function f of x is equal to ce to the power ax such that the graph f crosses y-axis at 2 and 1 and negative 5 is on its graph. I don't think I wrote the best sentencing or rephrasing of my question, but that's the question. I have a function of that form. We call that exponential function in general. There are this coefficient and this guy over there. Now, this is a fact. You know the type of such function. You only need 2 pieces of information about this function to be able to determine what are C and A. And where this comes from is just simple writing down these things. When a graph crosses y-axis at 2, how can I write that in terms of f itself? A function's graph crosses y-axis at 2. How can I write it in terms of function itself? Yes? It means that when you plug in 0 into x, you get 2. Yes? The other one is also there. So it means the other one also means that when you plug in 1, you get negative 5. Okay? So I translated those information in terms of the function. In this case, doesn't matter what is the function. That's always the case. Now I'm bringing in the form of this function, which is, okay, it has this form, so I can plug in 0 here. So ce to the power a times 0 is equal to 2. And this one here, I plug in 1 here, ce to the power a times 1 is negative 5. In other words, so I can say that I'm going ahead with these formulas. Look, a times 0 is 0. E to the power 0 is 1. So this is c equals to 2. The other one is this guy. C is equal to 2, so I can take that one already here. So this is 2. E to the power a is equal to negative 5. Wait. You know what? I am noticing now the mistake I made. This should have been negative 2. Sorry. I knew that I'm not doing something right there, but, and this means that otherwise it wouldn't be, there's no such function otherwise. So in this case, we get that e to the power a is negative 5 over negative 2, or that's the one. E to the power a is 5 over 2. What does that mean? What does it mean in terms of a? Yeah? What does it mean?
1 5 over 2.
Or, other way of asking that question is that how to solve such question. To get rid of e to the power something, you ln both sides. And remember that log base e composed with e to the power a, it's going to be a. And that's what you're looking for. So in other words, your function is negative 2e to the power ln of 5 over 2 times x. Yes, please.
How did you get the c equal to negative 2 again?
When you plug in 0, you get negative 2, yes? Plug in 0 here, a times 0, 0, e to the power 0, 1. There's no part of this one, and c is equal to negative.
Thank you.
Before you go, let me write this question down. This is one of the exponential equations. I would love you guys to think about this. Solve this equation. 4 to the power x minus 2 to the power x plus 3 plus 15 is equal to 0. What are the values of x, or value of x? Write it down, go home, think about them, and come back tomorrow. We are going to start chapter 2, limits, and have a great day.